Hi, welcome to Mr. Crow's Classroom. Today we're going to learn how to graph exponentials, so let's get started. Alright, so when we're graphing exponentials, we're going to go ahead and start with our simplest formula for an exponential, which is really, technically it's even simpler than this. It's really just b to the x, some kind of base, which is some kind of number, to the power of x. And that's really what makes this an exponential. The variable is in the exponent. Alright, but right now what I'm showing you is really just one thing we can change to this, which is multiply it by a number out front, some kind of constant we call a. But actually, we can make a lot more changes to this. In fact, in the exponent, we could subtract a number. We call that x minus h. And then on the outside, we could also add a number as well, and we call that k. Now, technically speaking, there's actually one more thing we can do. However, we're not really going to cover it today. The full transformation formula would also include this constant out front here in the exponent, which is a multiplier. And so if we have this, by the way, basically this multiplier out here, just in case you're curious, it would be a horizontal stretch or compression, or if it was negative, then it would be flipped horizontally as well, or it would be reflected over the y-axis, is the same way of saying that. But either way, we are not actually going to cover that today. Today we are only going to be interested in these changes, which is the a, the h, and the k. And if you are familiar with any other type of transformation with other types of functions, then yes, this a, the h, and the k, they actually stand for the exact same thing in all functions in algebra. Okay, so let's go ahead and cover what those are. And so something to help you out if you struggle with these is this acronym called HIVO. And HIVO means horizontal inside, meaning everything with the x, we would call that on the inside, that is going to affect the graph horizontally. In other words, up here with this x, everything up here is going to affect it horizontally. And then vertical outside stands for everything on the outside of that, not paired with that x, is going to affect the y, or the vertical transformations. In this case, the a and the k. Okay, so let's actually label these now. So H stands for a horizontal shift, and it is always the opposite of the sign. And the reason why it's the opposite of the sign is because imagine like H was -3. Well, that would be x minus -3. And x minus -3 would actually be x plus 3. So that is why it is always the opposite. Okay. The k right here is going to be a vertical shift, which is the same as the sign. And the a in front is going to be a vertical stretch or compression. Or if a is negative, then it will be flipped vertically as well. Or we would say it is reflected, reflected over the x-axis, is the same thing as saying that. Okay? All right, so let's continue on and take a look at an actual graph. So what you're looking at right now is one of our simplest graphs here, which is just y is equal to a base of 2 to the power of x. All right, in this case, a would be 1 out front. It would be 1 times 2 to the power of x, okay? But anyways, so this is what this graph looks like. And one of the, there's a few major points I want to start you off with. And this is really what you can start with all exponentials. There's really two major things we want to figure out. The first thing we want to figure out is this anchor point. Now, an anchor point, this is not the official term for this. This is just the term that I'm using to refer to it. But this anchor point is actually quite important. And also, the other thing that is important is this horizontal asymptote. So in order to describe to you, or at least show you how this affects the graph, we are going to switch over to a little demonstration. Give me 1 second. And so what you're looking at now is the exact same graph, which is f of x is equal to 1 times 2 to the power of x. And in this case, I went ahead and put a bunch of sliders on here. So I can change a from 1 to something else. I can change the base from 2 to something else. I can change the h value from 0, right now it's 0, to something else, and the k value from 0 to something else. And maybe we should start with the h's and the k's, and then we'll kind of move on to the stretching and the changing of the actual base. But anyways, things that I want to point out here is I want you to notice how the horizontal asymptote changes as we change this. And also right here, this little crosshairs, this is that anchor point that I was referring to. And the reason why we have this anchor point, by the way, is because anything to the power of 0 is 1. Okay, and so I want you to just think about that as I move this graph around. It doesn't mean that this is not going to change at all. It just is going to stay the same under certain circumstances. So first of all, let's go ahead and use, we're going to change k. So k is going to be a vertical shift up or down. So as I shift this thing up, as k goes up, the entire graph moves up, including the horizontal asymptote. And as it goes down, everything goes down as well. So what does that mean as far as the asymptote goes, first of all? So that means that under any type of like a parent function or where k is 0, the horizontal asymptote, the equation, is y is equal to 0 in all cases. In fact, if I change this base from 2 to anything else, let's go ahead and change that. So I'm going to increase it. So you can see as the base increases, this thing is going to, the graph is going to increase more rapidly. And as the base decreases, it's going to compress down. And as b becomes a fraction, it's actually even going to flip to the other side, or it's going to start decreasing, which makes sense, by the way. Like right now, this is b is equal to 1/2. That means as I move from left to right, as the x's go from lower numbers to higher numbers, that means that I'm multiplying by 0.5 every single time. So I'm getting half of the previous number, which is why it's decreasing. If I have a b of value of 2, it's increasing because as I move from left to right, I'm multiplying by an additional 2 with every single integer number. Okay. So anyways, as we change the base, you can actually see how this thing moves back and forth, but it definitely does not cross that horizontal asymptote. Okay, and even if only if I move the entire or shift the entire thing up and down is that going to change. Okay, it's still not going to cross that. All right, let's go ahead and reset this. And what I want you to take away from there is that basically the horizontal asymptote of the equation is y is equal to k. Whatever that k value is, that's what the horizontal asymptote is. And that's actually where I always start graphing horizontal functions. I always find the horizontal asymptote and I go ahead and plot it out. My next step is going to be to figure out what that anchor point is. But anyways, let's go ahead and do a horizontal shift now. And so you can see that is the entire graph is shifting to the left and right, including the horizontal asymptote. But notice it's not really changing because it's already just a horizontal line, right? But it is the whole thing is in fact shifting to the left and the right based on this h value. And then finally we have the a value. Now the a value on the outside is really this multiplier, and it's going to vertically stretch it if a increases. So the whole graph is going to stretch, or if it's decreasing, it's going to start compressing. And then if it's negative, it's going to flip over the x-axis or reflect over the x-axis. So you can see there's a is negative, and then as we move it up, it's going up and down. Okay, so it is vertically stretching and compressing in this case. All right, let's go ahead and set a back to 1. And actually, you know what? I'm going to set a to -1. And I think the last thing that we'll do to play around with this, I'll leave a link to this, by the way, so you guys can play around with this. But anyway, when this is flipped, if I start changing the base, it does the exact same thing. It's just on the other side. Or reflected over the x-axis. Okay, so as the base is changing. So like right now, the base is a fraction. So it is getting closer and closer and closer to 0 as we move to the right. And if b is above 1, then it's going to get bigger and bigger and bigger, or farther and farther and farther away from the x-axis as we move to the right. I shouldn't say bigger because this is a negative number. It's moving further and further away from that horizontal asymptote. Okay, so let's go ahead and we're going to go back to our notes. And let's go ahead and get to the point where we can actually like practice this. All right, so let's see. And we do have to round out a few more things here. So number one, how do we actually get this anchor? So that anchor point, as I said before, it really is important for us to figure out what value of x will give us an exponent of 0, because that value of x is going to be the x value of our anchor points. Now in this case, this is a very simple function. It's just x in the exponent. So that means at x is equal to 0 is going to give us an exponent of 0. So right here, you can see as x is 0, that is going to give us an exponent of 0. In other words, 2 to the 0 power, which means that the y value is going to be 1 for this anchor point. Now, what I want to show you here is you can actually, there is technically an equation for, or formula for this anchor point. But anyways, basically, if the exponent is 0, then that b, it doesn't matter what this b is, it could be anything under the sun, that is going to end up being 1. And so y would equal whatever that a value is, because it's a times 1 plus k. All right, and again, how do you figure out the y value? We'll simply plug in that x value to get the y, okay, for that anchor point. Now, let's go over a little bit harder example here, all right, just to show it, because it's not always where x is equal to 0 where the exponent is going to be equal to 0. Like in this case, we have 3 to the x minus 1. So what number is going to give us a 0 up in that exponent? Well, if x is equal to 1, then that means we'll have 3 to the 1 minus 1, which is 3 to the 0, which is equal to 1. So in this case, we would actually plug in x is 1, and when we do that, this will become 1, which is 2 times 1, so it's just 2, and then we get y is equal to 2 plus 5, which is 7 in this case. So 1 comma 7 would be our anchor point. Okay, and then after that, by the way, it's really easy to graph. You have your horizontal asymptote, so you put that on there. You have your anchor point, and it's really just a matter of stepping to the left and to the right on the x-axis and plug in those values to get some other y values. All right, and then you're pretty much good to go. All right, so real quick, just to repeat, how do we get the actual horizontal asymptote? Well, we just take the k value. It's just y is equal to whatever the k value is. All right, and then just to switch here, so this was y is equal to 2 to the x. Of course, it doesn't matter if we have like y is equal to 1/2 to the power of x. We still follow the exact same processes. An x value of 0 will give us an exponent of 0. So that'll give us our anchor point. After we plug it in, we'll get 0, 1. And then our horizontal asymptote is just the k value of y is equal to 0. Okay, so let's go ahead and do an example. And I kind of threw in as much as I could here. I guess the only thing that I didn't throw into this example was a negative out front, but really that would just flip this thing vertically or reflect over the x-axis. So how would we go about graphing this? Well, there are really a couple of different ways, and I like to use a combination of the two to kind of check myself, actually, for like a checks and balances. The first way I think about it in my head is I think about the transformations. Like, can I visualize what this is going to actually look like in my head? And then I go through a process of figuring out actual points, and then I plot them, and then I kind of reconfirm with myself, hey, did that match what I thought it was going to look like? So let's go through that process. So what is it going to look like in my head? Well, the first thing I do is I say, well, what is the parent function of this? The parent function, if I take away all of this extra stuff here, is really just the base to the power of x. In other words, y is equal to 4 to the power of x. So if I plotted that, it would look like this. 4 to the 0 power is your anchor point here of 1. 4 to the first power is 4. Let's see here. 4 to the negative first power is 1/4. My horizontal asymptote is going to be y is equal to 0 because this is 4x plus 0. So this is basically what the parent function is going to look like. And yes, there are an infinite number of parent functions for exponentials because there are an infinite number of bases. But I'm trying to use some simpler ones here. All right, now that I know what the parent function is going to look like, I need to think about what all of these transformations in this graph are going to do to the function itself. So for transformations, I have a value of 1/2 for a, which means that it's going to compress this whole thing. So all of these points are going to get compressed down by 1/2. Let's see here. My h value is positive 2, so we're going to go in the opposite of the sign. So we're going to go to the left 2, so everything is also going to shift to the left. And then finally, I have +1 for k, or I'm sorry, -1 for k, which means this is going to go down 1. So the whole thing will shift down by 1. And this is where I'm going to start. So I'm actually going to shift with that, start with that shift down, and I'm going to go after the horizontal asymptote. Okay. So that means that my horizontal asymptote is y is equal to -1. Whoops, let me go ahead and get rid of that parent function. Sorry. So that means the horizontal asymptote is y is equal to -1. And if we go ahead and plot that right here, put it on our graph, then there we go. So it's a dotted line. Yes, it's not an actual part of the solution set, but it is a part of the actual graph. We need to graph this as a dotted line. All right, and now what I'm going to do is I'm going to go ahead and create a table, and I'm going to first nail down that anchor point, and then I'm just going to move to the left and the right to get some other points after that. So remember, how do we get our anchor point? Well, what value of x is going to give us an exponent of 0? Well, in this case, -2 plus 2 is 0. So I'm going to go ahead and put that right here, -2, and then I'm going to plug it in. So if I plug in -2, that means I have 1/2 times 4 to the -2 plus 2 is 0, -1. And 4 to the 0 power is 1. So that means I have 1/2 times 1, which is just 1/2, -1, which is going to be -1/2. So at -2, we have the point -1/2. I'll go ahead and get rid of my work here so we can do the work for another one. And let's go ahead and plot this point. So at -2, I am at 1/2. All right, let's go ahead and step to the left, which is going to be a smaller number here. So I guess I'll put this up here. So I'm going to go to -3. And so if I plug in -3, that's -3 plus 2. So I have 1/2 times 4 to the negative first power. That's -3 plus 2 is -1, -1. And 4 to the -1 is 1/4 to the +1, or 1/4. So that's 1/2 times 1/4, -1. And 1/2 times 1/4 is going to be 1/8 -1. And 1/8 -1 is -7/8. Or if you like, you could say 1/8 minus 8/8 to get a common denominator is equal to -7/8. All right, so at -3, we have -7/8. Let me go ahead and erase my work, and we'll plot this point. All right, so at -3, we're down to -7/8. I don't know. I'm just kind of estimated to get as close as possible. I'm not going to go further to the left because this is going to get closer and closer to this horizontal asymptote, and I can't be very accurate there. So let's go ahead and move to the right. So I'm going to move over to -1 here and see what we get. So at x is equal to -1, we're going to go ahead and plug in -1 here. So that means I have 1/2 times 4 to the -1 plus 2 is 4 to the first power, -1. 4 to the first power is just 4. So 4 times 1/2 is 2, -1. There we go. There's a nicer number. 2 minus 1 is +1. Oh, I'm sorry. Yep, there we go. Yeah, sorry, I thought I made a mistake. So here we go. So at -1, we are at +1, and there's our point. And let's do one more. We'll go to -2 here. Oops, I'm sorry. I'm moving to the right. I need to add a number, so that's 0. So let's see here. So I have 1/2. We'll just do this one in our heads. 1/2 times 4 to the 0 plus 2. So that's 4 squared, which is 16. And 1/2 times 16 here is going to be 8. And 8 minus 1 is 7. So we have 0, 7. And we'll go ahead and plot that. And now we'll do the best we can. Remember, this gets as close as possible to this horizontal asymptote, but it actually doesn't touch it. So we'll just do the best we can. And then we're going to come up as this exponential increases because the base here is 4. So obviously it's going to go up pretty rapidly. All right, and there we go. There is our graph of our exponential function. So just a quick recap. For exponential functions, the horizontal asymptote is really important, and then that anchor point is really important, and then also just understanding what are the basic transformations in our transformation form. That way you can kind of have an idea of how this thing should end up looking in your head at the end. In this particular example, this thing does look like it got shifted to the left and down, and it was compressed a little bit as well. So anyways, so hopefully you found this video helpful and you have no problem graphing exponential functions at all anymore, and hopefully I see you in the next video. Have a good one. Bye now.